Hi, my name is Zach Espley, and I'm with the Department of Physics at UC Santa Barbara. I'm here to tell you about how we remotified our modern physics labs for instruction during the pandemic. When we started this, we asked ourselves how to best offer instructional labs remotely. To answer this question, we needed a set of criteria to define what we think the best labs are. This is what we came up with. We want students to work with their own hands, take their own measurements and not have data provided to them, have to deal with uncertainties in the measurement process, practice scientific note-taking, and be able to explore and experiment. With these ideas in mind, let's discuss the options available to us. From doing some research, there appears to be three main approaches: videos of the lab equipment in use, a simulated experiment, or having students work with a kit at home. The big problem with videos is that the students don't get to handle equipment themselves. If done well, there is some amount of data collection and uncertainty estimation that can be done, but not much. Students can take notes, but not on anything that they themselves are doing. And finally, there is no way to modify the experiment. Simulations are similar, except now students can make their own measurements. Additionally, a good simulation leaves room for exploration, and thus students can take notes on what they did. But simulations really lack in their uncertainty, with many simulations having no uncertainty at all. Finally, we have kits. We found kits hit all the criteria that we would want in a lab experience. So this is what we did for our sophomore labs. For mechanics, we had the students use items around their house to build apparatus and the smartphone app called Fifox to collect data. For E&M, we had the students buy kits from the internet and use a sound card as an oscilloscope to make measurements. But when it comes to modern physics, we did not have a way of making a kit. It just wasn't feasible to send students a Fraunkertz apparatus or build a photoelectric effect lab from household parts. So we decided to remotify the equipment that we already owned. This is what the rest of the slideshow will be about, so let's take a look at what we did. We created a low latency video stream and just put our equipment in front of it. We then added motors to all the knobs and all the controls that the students would normally interact with in person. We tried to make everything that you could move in the lab movable. Every button that you could touch, touchable. We tried to match the freedom that comes from being in person. Starting with the equipment we already owned, we designed and 3D printed custom modifications. Additionally, we had to purchase about $1,000 of support equipment per apparatus. Then we attached webcams to everything so that you could see it happening in real time. We did this for 5 of our sophomore modern physics labs: the photoelectric effect, the Fraunkertz experiment, diffraction and interference, atomic spectroscopy, and gamma ray absorption. We built all of this in a small, compact space in one room. The students could then do their labs while one person remained on site to monitor equipment. Now let's take a look at things from the student's perspective. First, if you have any questions or comments, you can reach us through this interface here. Next, you can see all the different tabs we have for all the information. I'm just going to go to the Labs tab where you can see the 5 labs that we offer. Let's take a look at the Fraunkertz lab. This is the typical view a student would see. Let me highlight the layout of this interface. First, we have the live feed in the center. In the bottom right, we have the equipment help. At the top are the camera controls. On either side are the main control panels, and the bottom is an occasional control panel. Now let's simulate what a student would do and take some data. You're going to start by turning on the electrometer. You'll see the screen start to respond here. While that boots, I want to highlight that this picture interface matches what is in the live feed, and all of the buttons are clickable. So I can set it to current, resistance, voltage, or anything else. For this lab, we need current, so I'll click that. Then we need to be in the nanoamp range, so I'll turn that down here. Next, I'll perform a zero correct. Notice how quickly the meter is responding to my clicks. Now I'll turn on the accelerating voltage, and you'll see this dial move here when it comes on. There it goes. You'll notice here it displays what the accelerating voltage currently is. Then notice if I click this arrow, it'll rotate a potentiometer and we'll see the voltage and current respond. Students will repeat this and create a plot of current versus accelerating voltage. Now let's look at some of the other ways students interact with the equipment. Here in the POTS view, you'll see most of the knob students turn to set up the equipment. They'll have to set the retarding voltage here, and you'll also notice the accelerating voltage potentiometer from before. Notice now when I click the arrow, we can actually see the knob turning in the lower left portion of the live feed. Here we have the tube view. This is just a live feed of the Fraunkertz tube that the students can look at. Next, let's look at the heat view. This is where the students can read the oven temperature here, and they set it by controlling this knob here. And that concludes our tour of the Fraunkertz lab. When remotifying the apparatus, we wanted it to match as many of our criteria as possible. In order to do that, we established 5 design principles. Let's look at each of these in detail. The first design principle is duplicate apparatus. We wanted 2 of each experiment so that students could work and troubleshoot together, but each student had the opportunity to explore and engage with the equipment at their own pace. Next is consistent presentation. Since we have 5 different labs for the students to perform in a quarter, we didn't want them spending much time learning the web interface for each lab. To lessen the learning curve, we created consistent design elements across all the labs. All of the labs have a centered live video feed, consistent switch design, and a common arrow theme for buttons and knobs. This allows students to intuitively know where to find things and what each interface does. Next, we have clear causality. It was very important that the students trust that the equipment was functioning properly, since the remote labs lack that tangible feedback students get in person. This was done in 2 ways. The first way was by reliably executing commands and visually showing the students the response in real time. The other way was by implementing an equipment helpline that students could use to get quick feedback on issues. If they thought something was wrong with the equipment, they could send a message here and get a quick response from someone in the room on the other side. Next, we want minimal automation in the labs. The students should have to manipulate the knobs and buttons by interacting with them on the website, as opposed to telling the computer what they want to measure and it performing the measurement for them. Students should have to collect the data and not the computer. To make this happen, we opted to have the students use the live feed to take measurements. For example, in our atomic spectra lab, we attached a webcam focused on the vernier scale to measure the angle of diffraction. Finally, we present the students with maximal options. We wanted to avoid forcing the students down a particular path by only letting them press certain buttons and knobs. With more options, students were free to explore the lab how they wanted. Additionally, this allows for students to make mistakes. As an example of this freedom, we made every button on our electrometer and multimeter clickable, even though the students only need to press a few of them to complete the lab. Now, let's revisit our remote instructional lab options and add remote labs to the list. With these 5 design principles, we think we're able to achieve 4 of our best lab criteria with remotification. Obviously, students couldn't handle the equipment themselves, but they did have to collect their own measurements. Since we were using actual equipment and instruments, uncertainty was just baked in. Students were able to take scientific notes on what they were doing, and with the freedom of the labs, they could explore and experiment. This is why we think remotification is the best option for modern physics labs. We were able to make 8 of our 10 apparatus in just 4 months with 3 people working part-time. Why was this achievable? Well, it comes down to 2 main things: cost and accessibility. On this slide, you see 2 tables summarizing the hardware and software that was used. I want to highlight a few things about these tables. First, on the hardware side, all the equipment we used is mass-produced, widely available, and can be at your doorstep within a week of ordering. Next, notice for the hardware, all the equipment is relatively cheap, and the software is all free, or free for universities. Lastly, for both the hardware and the software, you can see that nearly everything is well documented and most are open source. All of these elements put together make doing a project like this very accessible even for non-experts in programming, robotics, and web design like ourselves. In conclusion, I would like to highlight our main takeaways. Firstly, modern physics labs are an excellent choice for remotification. They cover most of what we want out of a good lab and do it affordably. With these labs, we are able to service up to 240 students per quarter. Next, we think remotified labs have a purpose in the post-COVID world. They can provide improved access to students and extended time with the equipment for disabled students. Additionally, we hope to offer access to universities in other countries that are still suffering from the pandemic. Next, we think these labs are a good educational experience, but we think there needs to be some sort of PER work done on remotified versus in-person labs. If anyone is interested in working with us on this, please reach out. Finally, we are excited to work with any other universities that would like to copy what we did and any other corporate investments. Lastly, we would like to thank everyone who made this possible. Thanks to the people who helped, especially our 2 undergrads, Sharon and Balfred, and the organizations that provided the support. If you'd like, go to the link here and check out the labs for yourself.